Hello there. Hi, I'm Mr. Math Guy, and today we're going to be looking at a 10-minute video on tangents. Let's take a look at a couple of definitions here. First, we have the definition of a secant line, or secant. A secant is a line in the same plane as a circle and intersects the circle in exactly 2 points. So if I'm wanting to take a look at maybe what a secant line is, secant line intersects a circle in 2 points. So right there and there's a secant line. So we can see it intersects the circle right there and right there. When we talk about intersects the circle, talking about the outer ring of points, not the interior of a circle. All right. So 2 points. Now a tangent then is a line in the same plane as a circle. But it only intersects the circle in 1 point. So a secant or a tangent line might run something like this. Intersects the circle like maybe right there in only 1 point. So we have a secant line, and here we have a tangent line. Now, it's pretty easy to see the next definition here. It's called the point of tangency. So I'm not going to write out what the definition of a point of tangency is, but you can see the point of tangency is going to be where the tangent line intersects the circle. So it's called a point of tangency. And generally these are very important points. So the point of tangency right there. Let's take a look at a theorem that we may have. Let's say we have a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So here is what it might look like. We have a tangent that's drawn, intersects the circle in exactly 1 point, and we have that point of tangency. What it's going to be perpendicular, or it's going to form a right angle to the radius that's drawn. So no matter where you draw a tangent line, its point of tangency will be perpendicular to the radius of the circle. We have another theorem that says if a line is perpendicular to a radius at a point on the circle, then the line is a tangent to the circle. Now notice, this is simply just the converse of the previous theorem that we had. So it may look like this. If we have a line, and we know that this line is perpendicular to the radius of the circle, then we can call this a tangent line. We know it's a tangent line, and that right there would be the point of tangency. The next theorem we have says that tangent segments extending from a given exterior point to a circle are congruent. So if we have an exterior point out here, we'll call it point P, then the tangent segments that are formed from this point, hopefully I can draw these somewhat accurately. We have a tangent line there, and we have another tangent line here. Then these tangent segments extending from a given exterior point to a circle are congruent. That means from the points of tangency, right there to P, and right there to P, those two distances are congruent. Now, those lines extend forever, but if we're just talking about this particular part right there, then these two measures, this part and this part, would be congruent. That's what that theorem is saying. Now, I didn't take the time to prove these theorems, but they are proven. I just gave an explanation of what the theorems are. So we have a definition here. This one's called a common tangent. A common tangent is simply a line that is tangent to two coplanar circles. Circles that are in the same plane. So we have these two circles in the same plane, and we have a line that is tangent to both of the circles. This would be called a common tangent. It's tangent at each circle. It intersects each circle at one particular point. So here's a common tangent right here. We could have another common tangent, maybe right here. It goes across there, intersects there's tangent, and there's tangent. So that would be a common tangent as well. Here we have another definition and a little drawing underneath to kind of explain it. It says tangent circles, they are coplanar circles, circles that are in the same plane, that are tangent to the same line at the same point. So you have these two circles, this black circle that I have and this green circle that I have. They are tangent to the same line at the same point of tangency. So these are said to be tangent circles. Let's look at two more ideas real quick. We have internally tangent circles, which are tangent circles on the same side of a common tangent. And then we have externally tangent circles, which are tangent circles on opposite sides of the common tangent. So it might be best to just kind of look at an example here. If I have a tangent, and hopefully I can draw this somewhat accurately, that's not bad. If I have a tangent line here, we've got tangent circles. The blue and the purplish one, those two circles, they're on the same side of the tangent line. They're tangent circles. They both intersect at that same point of tangency. They're on the same side of the tangent line. Those are called internally tangent circles. Internally. Now, the purple one and the green one, or the blue one and the green one, those are on opposite sides of the tangent line. They're still tangent circles, but since they're on opposite sides of the common tangent, those are said to be externally tangent circles. So internally, they're on the same side of the tangent, and externally, they're on opposite sides of the tangent. Let's take a look at maybe some questions that may arise from problems with tangents and things like this. First question I want to ask is, what kind of triangle is triangle LBF? Triangle LBF. Well, if you look at LBF, well, if you notice, this is a radius and a tangent line. Those are perpendicular to each other, so they form a right angle. So triangle LBF would be a right triangle. And so would triangle LEF. That would also be another right triangle as well, since a radius and a tangent line intersect to form a perpendicular angle, to form a right angle. What if I had a question that said something like, FE, let's say that FE is 23 units long. If FE is 23 units long, then how long is BF? Well, according to one of the theorems, that if we have tangents to the same circle at an exterior point, and this exterior point is F, then the tangent lines, or tangent segments, are congruent. So if FE is 23, then BF will also be 23. The distance, the length of those measures will be the same. Let's just take a look, a quick review here. Just ask some questions. If I ask you, what kind of circles are the blue and purple circle? Are they internally tangent circles, or are they externally tangent circles? The blue and the purple one. Yeah, the blue and the purple would be on the same side of a tangent line. Alright, if I have this tangent line, hopefully I'll be able to draw it somewhat accurately. Something like that. The blue and the purple are on the same side of the tangent, so those are internally tangent circles. What if I said, what kind of circles are the orange and yellow? The orange and yellow, are they internally tangent circles, or are they externally tangent circles? Well, they're on opposite sides of the tangent line, and they're tangent circles, so they would be externally tangent circles. Let's take a look at maybe some more examples here. How many tangent lines do you see here? You see two tangent lines. And what are those two tangent lines? The two tangent lines are line A and line C. They intersect circles at only one point. Now, we have two other kind of lines here, lines B and D, and those intersect circles in 2 points. So those lines, lines B and D, are called secant lines. So this is just to distinguish the difference between tangent and secant lines. And C, line C, also has a special name. Since it is tangent to at least two coplanar circles, it's also called a common tangent. I hope this video on tangents helped you understand what tangent lines are a little bit better. Thank you for watching. God bless.